Okay, the streaming started and I am pasting the video link in the chat. Okay, so in week 4, what are the things we have seen so far? We have seen how a dot product is defined in R2 and in C2, right? So dot product takes two vectors from R2 or C2 and maps it to the corresponding scalars, right? And then we saw what is the magnitude of a vector, distance between two vectors, and angle between two vectors. So up to this we have covered so far. So these are the topics which we have already covered. Okay. So today I will complete up to adjoint, and if I have time, I will also complete range and null of an operator. Okay. Fine. So a quick glance on the topics covered in the previous class. So what is dot product in R2? So if you take two vectors from R2 and u dot v is just x1 x2 plus y1 y2. In C2, you have to be careful. You have to write u1 v1 bar plus u2 v2 bar. Okay. So what are the key properties of dot product in R2 as well as in C2? So in R2, you have the symmetry property, which is u dot v is equal to v dot u, and conjugate symmetry in C2, which is u dot v is equal to v dot u bar. Okay. And in both the scenarios like R2 and C2, in both the cases, you have the linearity in first argument. Okay. And in R2 you have linearity in second argument as well, but in C2, since we have in the definition we have the complex conjugate for the second argument, so because of that we have conjugate linearity in the second argument, so the scalars come out with a conjugate. And in both the scenarios we have positive definite property, so that is u dot u is non-negative, and it will be 0 if and only if the vector itself is 0. Okay. So these are some important properties we have seen about dot product. Okay. And then we saw what is magnitude of a vector, which is nothing but square root of u dot u. Okay. And the same thing goes for C2 as well. And for distance, you have to calculate what is norm of u minus v. So norm of u minus v in terms of dot product, it is simply u minus v dot u minus v. All right. Just like here, instead of u, you are having u minus v. Okay. In C2 also the same thing goes. And for angle between two vectors, in R2 you have u dot v cos theta is equal to u dot v by norm u norm v. And in C2 you should take the real part of u dot v divided by norm u norm v. Okay. Then we saw what are orthogonal vectors. So in R2, do you remember if two vectors are orthogonal, that is their dot product is 0, what is the angle between those vectors? Can anyone remember and tell?
190 degree.
Yeah, so it is plus or minus 90 degrees, right? Okay. And also we saw that orthogonality implies linear independence, right? If two vectors are orthogonal and non-zero, then they must be linearly independent. Okay. What about the converse? Is the converse true? We saw that the converse is obviously not true. So these two, you see that they are linearly independent, but they are not orthogonal, right? And then we saw what are orthogonal bases and orthonormal bases. So a basis is said to be orthogonal if the vector basis vectors u and v are perpendicular, that is orthogonal. And it is orthonormal if, in addition to the orthogonal condition, you have their norms to be equal to 1. So a vector is said to be normalized if the norm of the vector is 1. Okay. So if u and v forms an orthogonal basis, how can you find an orthonormal basis? I have already told it in the previous session. Can anyone tell? How can we
Then we
form?
will divide it by its magnitude.
Exactly. Good. So we divide by its magnitude. So you have u by norm u, comma, v by norm v. Okay, fine. Okay. So the next topic we are going to see today is coordinates of a vector with respect to orthonormal basis. So before even moving to this, quick recall. So let us say you are having this basis E1, E2. Okay.
Madam, can we get this document, is this PDF, whatever you are presenting, so that it will be handy for us also?
Every time after the right after the session, I am actually sending it to Shubham, and
Okay,
I'm
madam.
sending it to you. Okay.
Okay.
Fine.
Thank you, madam.
Okay, fine. So let us consider a vector x comma y. Now, what are the coordinates of this vector with respect to the canonical basis? What are the coordinates? This is the most simplest case. You should answer immediately. What does it mean by coordinates of a vector with respect to a basis? So suppose you have a basis, first of all,
X1 and Y2.
sorry.
Ma'am, X1 and Y2.
So that is how you are expressing this.
X1 plus Y2. Yeah.
Yeah, x e1 plus y e2. So here you see that x and y are called the coordinates. Okay. So here it is very straightforward. But for example, if we have a different example, maybe 1 comma 1 and 1 comma minus 1. Now, what are the coordinates? We don't know, right? It can be anything. So we have to find what are the coordinates. So if you call this as u1, u2, then what are the coordinates? They are some alpha and beta which satisfies this equation, right? So this alpha and beta are called the coordinates of x comma y with respect to this basis now. Okay. So what is mean by coordinate? You all remember now. So coordinates means whenever you have a basis and you write it as a linear combination, the coefficients are the coordinates with respect to the given basis. Okay, fine. Now with this, now let us see you have a basis. Okay. Now we are going to find the coordinates of a vector w1 w2 with respect to b. Okay. So now what are the coordinates? So w you can write it as xu plus yv. So x and y forms the coordinate. So how are we going to find the x and y here? Okay. So how are we going to find how? First of all, what is this w equal to xu plus yv? Let us see. So w is w1 comma w2, and xu is x is a scalar. Now remember that x is a scalar, u1 u2 plus y times of v1 v2. This is what we have. Okay. Now you this simplifies to xu1 plus yv1 plus x u2 plus yv2. Okay. So this we can write it in the matrix form. You will see that this is xu1 plus yv1, and then this is xu2 plus yv2. Okay. So this is same as this, right? This is the matrix form of this expression here. Okay. And that is equal to w1 w2. Okay. Fine. So do you all understand how we got this from here? Yeah.
Yes, ma'am.
Okay. Fine. So now let us say that this B is orthonormal. So if B is orthonormal, what are the things we know? You have U and V. So if it is orthonormal, you know that U dot V should be, what is U dot V?
0.
And what is norm U?
1.
Norm V is also
1.
1. So these are the things we know if B is orthonormal. Now, how to find x and y? How do we usually find these coordinates? Can anyone tell? Suppose you are having some basis like this and you are having some vector. How will you find the coordinates? Can anyone remember? Or just by looking at this, what is your guess? If you don't remember, also from here you can guess. What is that we have here? We will have something like this. What is this we have here? This is what exactly we will have in this scenario. What is this? This is a system of,
Linear equation.
yeah, you have a system of linear equations to solve. So once you solve the system of equations, the solutions will give you this coefficients x and y, right? But when you have an orthonormal basis, it is not going to be that difficult like any usual basis. Suppose you are having a very normal like basis which is not orthonormal, then you may not have some advantages. So what is the advantage of having an orthonormal basis? That is what we are going to see here. Okay, so now W is this xu plus yv. Okay, now we want to find this x and y in this expression. Okay, so first step is that we are going to take the dot product of W with u. Okay, so W dot u is xu plus yv dot u. So you can use the linearity in the first argument and split it. So now you know that u dot u is 1. What is u dot u? What is the relation between norm and u dot u? Can you remember? I just told in the beginning of the session also. Norm u is equal to,
Under root of x square.
it's simply
This one.
u dot u, right? So now if you know that norm u is equal to 1, then you also know that u dot u is also equal to 1. All right, and then you know that if u dot v is 0, then v dot u is also 0, right? So that you know that the first case here it is 1, and in this place it is 0. Okay, so what will be w dot u? W dot u is x times of 1 plus y times of 0, which is simply x. So what is the x coordinate? X coordinate is simply w dot u. You don't have to solve any system of linear equations to get the answer for what is x. What you have to simply do, you have to simply do w dot u, and then you will find x. That's all, as simple as that. Okay, the same thing you have to do for y also. So without even doing any calculation, can you guess what can be y? Can you guess? See, x is w dot u. So what can be
W
y?
dot V.
That's all, right? So the same similar steps you will have. Then you see that this part is 0 and this is 1. So you have y is equal to w dot v. Okay, so what is that you have here? You have x is equal to w dot u and y is equal to w dot v. This is very useful when you solve problems. Okay, you can save time if you know that you have a orthonormal basis. You can save time if you know this. Okay, fine. Now find the coordinates of 3 comma 5. Okay, so this 3 comma 5 is your w now. So this is your w. This is your w1. This is your w2. Okay, this is your w with respect to the following basis. Okay, so you have your u and v. Okay, so this is your u and this is your v. Now can you tell me how to find the coordinates of this w with respect to, let's do the first one. Can you tell me what's the steps? What are the steps? You know already, I have just the formula written here only. So the coordinates of 3 comma 5 I want. So first of all, I write 3 comma 5 as x times of u plus y times of v, where u is this and v is this. Okay. Now, what is the next step? What is x then? First of all, this u and v, does it satisfy the orthonormal property? What is u dot v?
0.
What is norm u?
1.
1.
And what is norm v?
Also 1.
Okay. So now you see that this is an orthonormal basis. This is an orthonormal basis. Okay, so this I am writing in short as orthonormal basis. Okay, so this is an orthonormal basis. So I can have x is equal to, I call this as w. So w dot u and y is equal to w dot v. Now can you tell me what is x and y here? Calculate and tell me. Everyone try to calculate. This is a very simple question. I'm giving everyone time to calculate this. Everyone try it out. What's the answer? If you want, you can put it in chat. If you don't want to tell it, you can also put it in chat.
I'm 3 by root 2, comma 5 by root 2.
Is it comma? We are doing dot product.
Oh, sorry. 3 by root 2 plus 5 by root 2.
So what's the answer?
8 by root 2.
Okay, it's 8 by root 2.
2 and
Okay. What about y?
3 by root 2 minus 5 by root 2.
So,
minus 2 by root
Minus
2
2.
or equals to minus root 2.
okay. So this is what you are having here. Okay. So here you will have 4 root 2 and here you have minus root 2. Okay. Fine. So this is as simple as that. Now I'm telling all of you to do the next part by yourself. So what you are going to do is that you are going to take your u as cos theta, sin theta. Your v is minus sin theta, cos theta. Now, how will you check if it is orthonormal? What are the conditions you need to check that this u and v forms an orthonormal basis? You tell me.
Ma'am, norm u and norm v should be 1 and u dot v should be 0.
U dot v is 0,
0.
right? Okay, fine. So, what is u dot v here?
Zero.
Right? So, you get u dot v is 0. What about norm u?
1.
Norm u is 1 and norm v?
Also 1.
Okay, so you see that this basis actually is an orthonormal basis. So since this is an orthonormal basis and you have w is equal to 3 comma 5, and if you write x w is equal to x times of u plus y times of v. Now how will you find x and y? What is the formula? X is equal to
W times u.
not w times w dot u,
Yes, sir.
and y is equal to w dot.
W dot U.
Okay, now calculate x and y. It is
3 cos theta plus 5 sin theta.
and y is
Minus 3 sin theta plus 5 cos theta.
okay, good. So if you put this x and y here and multiply with u, you can see that it will give you the w. You can, so if you have any doubts after finding the answer, you can also put it back here and see whether you are getting back w. Okay, you can check it if you want. Okay, so up to this, is it clear for everyone? Yes.
Yes, ma'am.
Okay. Okay, so we are moving to the next concept, which you already have some idea. So we are just going to give some name for it. That's all. Okay. So now I actually wanted it to be this vector, but anyway, yeah. So what is this vector here? This one. What is this vector here? Yeah. What is this vector? Is it that difficult?
Ma'am,
What is this point?
1 1.
Yeah, that's all right. It's simply 1 1. So let's call this to be u 1 comma 1. Okay. Now what are the vectors which are orthogonal to u? What are the vectors which are orthogonal to u? We have already solved this problem in the previous session. how will you find vectors which are orthogonal to u? So for that, what you usually do is that,
And we will take dot product.
yeah, so you take dot product and equate it to 0. So you see that you have x plus y is equal to 0. So you have the equation y is equal to minus 6. So all such x comma y are the vectors which are orthogonal to u. So it is nothing but this line y is equal to minus 6. Is that correct? Yes?
Yes, ma'am.
Okay. Now let us consider this vector. What is this vector here? Let's call this v. What's this vector?
3,4.
Okay. Now what are the vectors which are orthogonal to v? X comma y dot product with 3 comma 4 should be 0. So you should have 3x plus 4y is equal to 0. So does the point 4 comma minus 3, you see that here you have 4 comma minus 3. Does the point 4 comma minus 3 lie on this line? Yes?
Yes, ma'am.
Okay. What about the point minus 3 comma, sorry, minus 4 comma 3? Does this point lie on the line? Yeah?
Yes, ma'am.
Whether it satisfies the equation. So you see that this line is consisting of all the vectors which are perpendicular to this vector. So which are orthogonal to this vector. So given a vector, in general, what is the set which can represent the vectors orthogonal to that specific vector? Tell me the answer. You take, let us say you have some vector u in R2. What are all the vectors? What is the set which consists of all the vectors orthogonal to this vector v? Tell me. When you have u, you had this straight line. When you had v, you had this straight line. Now I am taking any vector in R2. What is going to be the set of all vectors orthogonal to v?
Points on the line, you mean?
It is going to be some straight line which passes through
Origin.
origin, right? So you take any vector, then the orthogonal set of all vectors which are orthogonal to that vector forms a straight line. Okay. So here is a name for such vectors orthogonal to a given vector. So the orthogonal complement. So this is the name we are giving for the set. Okay. Nothing new here. The orthogonal complement of a vector v denoted by v perp. Okay. So denoted by v perp. So this is defined as the set of all vectors that are orthogonal to v. This notation is perp. Okay, so all the vectors that are orthogonal to v. So here you take the vector v, the v perp is set of all u such that u dot v is equal to 0. Okay, so the definition is clear, right? Now suppose for example, let us say you have the vector v here. Then what is your orthogonal complement of v? It is this line which is perpendicular to this vector. Okay, so u dot v implies that u dot cv is equal to 0 for all c, scalar c. So it means what? This orthogonal complement of the vector is a line which passes through origin and the vector v, the whole perp. Okay, so here you see that if you take any vector v or any vector lying on this line joining origin and v, that is what is given here. So v perp is same as, this is same as cv perp. That is what is given in this line. Okay, so if you take any other vector lying on the same line, that orthogonal complement is also going to be the same. Okay, fine. Now, the orthogonal complement or dual of a subspace denoted by S perp is defined as the set of all vectors that are orthogonal to the vectors in S. So exactly the same definition. So now instead of just a vector, we are talking about orthogonal complement of a subspace now. Here we talked about orthogonal complement of a vector. Now we are talking about orthogonal complement of a subspace. Okay, fine. So far, are you all following? Yeah? Okay. Okay. So before looking at what are all the orthogonal complements of the subspaces of R2, do you all remember what are all the subspaces in R2? Let me not show the subspaces. You try to tell me what are all the subspaces in R2. Tell me quickly.
Origin,
Yes.
line through origin.
Line passing through origin and the whole space
All
infinite.
other.
Yeah. Okay. So now subspaces and their duals in R2 we are going to see. So the orthogonal complement of a subspace is a set of all vectors that are orthogonal to every vector in U. Right? Now what are all the subspaces in R2? We know the zero space. Any line that passes through origin, for example, the x-axis, the entire space. So these are the possible subspaces of R2. Right? These are the only subspaces. Now, what is the orthogonal complement? This is the orthogonal complement. Set of all V in R2 such that V dot U is 0 for all U in U. Okay. Now, let us say your U is 0. So, now your U is 0, comma 0. So, if your U is 0, comma 0, what is your U perp? What are all the vectors which are orthogonal to the 0 vector? So this U perp is the set of all vectors such that V dot 0 is 0. What is the answer?
Ma'am, entire R2.
Yes, it is going to be entire R2. You take any vector, the dot product with it is 0, right? So you see that it is entire R2. Okay? You all understand, right? Okay? Fine. So now this one we already know the answer. For one-dimensional subspace. So what is one-dimensional subspace in R2? So it is span of U. So you take one vector and take the span. So it means what is the scenario? What is the orthogonal complement of this particular vector? We already know. So now we also saw that orthogonal complement of this vector or any CV is going to be the same, right? So here if you take span of U, okay, then to find orthogonal complement we need to find all v such that v dot u equal to 0, and that is going to form a straight line. Okay, so this equation describes a line through the origin in R2 which is perpendicular to u. Okay, for example, if u is 1 0, you know that the orthogonal complement is the y-axis. 1 0 means the span of u is the x-axis. What is span of u in this case? The x-axis. Right? What is the orthogonal complement of x-axis? Obviously y-axis. Same way, if you take u is equal to 1 comma 1, can you tell me what is span of u? What is span of u? It's okay even if it is wrong, just tell me. What is the span of u?
Scaling, right? C into U. U.
Yes, yes, the set of all c times of u where c is in R. What does this form?
It's a line through.
Right? It is a line. That is correct.
Line
See,
through origin.
but can you tell it precisely? See, it is a set of all points c comma c if you write precisely, right? U is 1 comma 1. So it is c comma c. Now, what are the points? Like you have to tell it in terms of an equation. Try to tell it in terms of an equation. So both your x and y are same. What is the line which satisfies this
Y
property?
equal to X.
That's all. Okay. So the line y is equal to x. Okay. So that forms that is your span of u. So if you take the line y is equal to x, which I have mentioned actually here, so this is actually your line y is equal to, so if you take this, okay, this is actually your y is equal to x. All the points connecting this. Okay, so this is your y equal to x. So when you had y is equal to x, what was the orthogonal complement we saw? We already have seen the answer, right? It is y is equal to, what's the
Minus
answer?
x.
Minus x, right? Okay, so you now know how to find the orthogonal complement easily, right? Okay, so now if your u is entire R2, so in this scenario, your capital U was span of U, right? Now in this case, your U is entire R2. So what can you tell about U perp? So you want, so let us say U perp here by definition is the set of all V in R2 such that V dot U is equal to 0 for all U in R2. What is the vector which satisfies this property for all the vectors U in R2? See here, first of all, one thing you should note, whenever you have this V dot U equal to 0 for all U in R2, V is also, yeah, what is the answer?
And zero vector.
It is just the zero vector. Only the zero vector can satisfy the property that the dot product with it is 0 for any U in R2, right? So here you see that it is just the singleton 0. Okay, so U purpose singleton 0. So what are the scenarios we have seen? In the one dimension, in the zero dimension case, it means the subspace is the origin. There the dual was the entire plane. And when the dimension is 1, that is you have a straight line through the origin, then the dual is a perpendicular line through the origin. And when the dimension is 2, that is the entire R2, then the dual is again origin. Okay, so what are some things which you can observe from this table? What is the dual of a subspace? Is that also a subspace? Is entire plane a subspace?
Yes, ma'am.
Is a line through origin a subspace?
Yes.
Is origin a subspace?
Yes.
So the dual of a subspace is always a subspace. Okay. Now what is the relation between the dimensions of these two spaces? You can see. What is the dimension of this space? This one? 0.
0.
And what is the dimension of this?
2.
2. So you get 0 plus 2 is 2. Now what is the dimension of this space?
1.
And this one?
Also 1.
So 1 plus 1, again you get 2. And what is the dimension of this?
2.
And here?
0.
0. So again you see 2 plus 0 is 2. Okay. So you see that the dimension of the subspace. So what is that you can see? Dimension of the subspace plus the dimension of the orthogonal complement is 2. Okay. And one more thing you see, let's say your U is origin, for example. Okay. Then we know that the dual is the entire plane. Now what is the dual of the dual? So this is your dual. So here it is there. What is the dual of the dual?
Previous one.
Okay, you are getting back the same, right? So when you, the same you can observe with entire plane also. The dual is origin, and then origin's dual is entire plane. And then you can do the same with line also. The dual is a perpendicular line through origin. Again, for this, it is the perpendicular line to this line, which is again this. So the dual of the dual is again the same space. So these are the properties we can observe from here. The dual S perp is a subspace. Dimension of S perp plus dimension of S is 2. Dual of dual. Okay, S perp, the whole perp is S. Okay, these properties, are they clear? Yeah?
Yes.
Yes, ma'am.
Find the duals of the following subspaces or subsets. So you have span of 1 comma 2. How do you find the dual of this? So this is your U. Now U perp is the set of all x comma y such that x comma y dot 1 comma 2 is equal to 0. Can I write it like this?
Yes, ma'am.
Yes.
So it means it is the set of all x comma y such that, can you complete this? What is the equation you will get from here?
X plus 2y equals to 0.
X plus 2y is equal to 0. Okay, so you see here you have the equation x plus 2y is equal to 0. So when x is equal to 2 and y is equal to minus 1, you get it to be 0. Okay, fine. So now can you find what is the dual of this space? So first of all, can you tell me how will you write u here? What is your u?
Ma'am, 1 minus 1.
Okay, you want to tell it in terms of span? Okay, fine. So it is the span of
Sorry, minus 1 1. Yeah.
1 minus 1 or minus 1 1. Both are same. Okay, so it is the span of this vector. So find what is u perp using the same technique. What will you get? What will you get? What's the answer?
X minus y equals to 0.
Yeah, x minus y equal to 0. So x is equal to y. Correct, Akash. Okay, good. Okay, so I see a few people are actively participating. Akash, Dhanraj, Yash, Arijit. There was another student who was active in the previous session. Where did he go? Or what was his name? Akash only, right? Akash Patel. And some other students were also there. Chirag also answers sometimes, but sometimes he is gone. What about the others? Why you are not participating? You don't understand, or you are just attending the session for attendance, or what's going on? Why the others are not responding? I want to know. You can tell whatever is the reason, you can tell. You don't understand, or you don't have sufficient time to complete it. What is the scenario? Like, if there is some scenario where I can help you, I can do something. That's why I'm asking. Any comments? No? Okay, so whoever is answering, very good, keep it up. And those who are not answering, either tell me your suggestion so that I can help you to answer, or it is up to you. Okay, fine.
Here the points on the x plus y, right? We are finding the dual for
Yes.
the all the points on
Mhm.
x plus y. So do we need to write like that? So x comma y such that x minus y equal to 0, right? That's what.
You can write in that way as well. So both are correct. You can write u is first of all the set of all x comma y such that x plus y is equal to 0, which can be rewritten as set of all x comma y such that y is equal to minus x, right? So
No,
which,
I'm talking about the other the
yeah,
dual. Also, we need to write in this
yes,
form, right?
yes. So now u perp, you can write exactly like this, and you can see that it is set of all x comma y such that x minus y is 0, right? It means what? It is the set of all x comma y such that y is equal to x. So it is going to be set of all x comma x simply, where x is in R. So now you can easily write the vector. So whatever form you want, you can obtain from here. That's what I'm trying to do
Okay.
here. You can write it in this way also if you want. Okay. So here you see that this is 1 comma 1. So this is your u perp, and this is your u. Okay. These are the perpendicular lines through origin. Okay. Now see, you have this 2x plus 3y equal to 7. Now, is this a subspace? Is this a subspace?
Yes.
Yes. Does it pass through origin? See,
No, ma'am.
this
No.
is your line 2x plus 3y is equal to 7. Does this pass through origin?
No, no.
No, right? For example, you take this point. So what is this point? 2 comma 1. You put here, it satisfies this equation. So it means this is the correct line. It does not pass through origin, right? So if it does not pass through origin, can it be a subspace?
No.
It is not a subspace. So even though it is not a subspace, we can still find what is the orthogonal complement using the exact same definition. Okay. One thing you should understand is that if a line is perpendicular to this line, then the same perpendicular line is perpendicular to any line parallel to this. Do you agree with that? Okay. Do you agree? Let me repeat the statement. Let us say this is line 1. Okay. So what I am saying is that suppose, let's say this is L2. L2 is perpendicular to L1. Then L2 is perpendicular to any line parallel to L1. Is that correct?
Yes, ma'am.
So that is what we are doing here. So now we know that if it passes through origin, it is a subspace. Then for us, it is easier to compute. That's all. Now you take the subspace which is passing through the parallel line which passes through the origin. So it becomes a subspace. Now find the dual. Then you know that that line is also perpendicular to L1. Okay. So now you have, let us say your U is set of all x comma y such that 2x plus 3y is equal to 0. Okay. So now you can maybe rewrite this as set of all x comma. What is your y from this? Can you tell me? What is your y? How can we rewrite in terms of x? Minus.
Minus
Minus 2x
2x by 3.
3.
Okay. Fine. So you see that it is span of 1 comma minus 2 by 3. So just for our computational purpose, what is the vector we can choose instead of this fraction? If I don't want a fraction for easier computation, what is the vector I can choose? How will you remove this fraction?
3 minus 2. 3 comma minus 2.
Minus
You can
6.
multiply with a scalar which nullifies this denominator, right? So for example, if you multiply with 3, you get this. Okay, now you can easily find what is your U pub. Now what is your U pub? It is nothing but the set of all x comma y such that x comma y dot product with 3 comma minus 2 is 0. So it means what is the equation we are getting? X comma y such that 3x minus 2y is 0. Is that correct? Yeah. So this is the line which we are looking for. So here, for example, this is the line I have plotted. See, you have this point 2 comma 3, for example, here. You substitute 2 and 3, you see that it lies on this line and it passes through origin. So this is the line we are looking for. Okay. Is that clear? Yeah.
Yes, ma'am.
Okay. So how to find the orthogonal complement? By now, everyone should be having a very clear understanding. No one should make a mistake in this part. All right. Okay. So next we are going to see inner product as a linear transformation. Okay. So how can we see inner product as a linear transformation? So let's start with R2. Let's consider two vectors, P and W. We know how dot product is defined in R2. This is how it is defined. Now, how are we going to interpret this dot product as a linear transformation? We are going to fix one of the vectors. Okay, we are going to just fix one of the vectors and keep the same definition. Then it becomes a linear transformation. How? See here. So define the linear. Now you have TW is a linear transformation from R2 to, where is this what is the codomain? Can you tell from this definition? What is the codomain? Can anyone tell? What is the codomain? Codomain means, so if you have a function, you know that this is the domain and whatever is here is called the codomain. So here, this value, does it lie in
Ma'am, R.
R2? Yeah. So here your codomain is R. Okay. So this is a linear transformation from R2 to R. Okay. So now this linear transformation is defined in this way. TW of V is V dot W. That's all. Okay. And how do you check that function is a linear transformation? What are the conditions need to be checked?
Closed under addition, closed under multiplication, and
That's all.
it's contain 0, 0.
Yeah, that will automatically follow if this satisfies this. So you have TW of V1, V2 should be TW of V1 plus TW of V2, right? And also you should have TW of AV is equal to A times of TW of V. Now, can you see that it straight away follows from the linearity in the first argument? Because what happens to T, for example, TW of AV, it simply becomes AV dot W. So you know how to apply linearity in the first argument. So you can take this A commonly and then V dot W, that will give you TW of V. Same way you can do it here also. So you can see that this straight away follows from the linearity in the first argument of the dot product. Is that clear to everyone? That this is a linear transformation because of the linearity of first argument in dot product. Okay, good. All right. So once you have a linear transformation, you know that there will be a matrix representation. So what is the matrix representation of this particular linear transformation? So V dot W means this is what you are having. Okay. So when you are writing this as a linear transformation with matrix, then you can take this form. How we are taking this form? Both are same, right? So what is the dot product of these two? You are going to, when you multiply, you are going to get V1 W1 plus V2 W2. Here also you can see that it is the same. W1 V1 plus W2 V2. Nothing has changed. Correct? Okay. So here the matrix is W1 W2. How? So how do you usually find the matrix representation with respect to canonical basis? Can anyone tell? How do you usually find the matrix representation of a transformation using canonical basis? All of you submitted week 3 assignment. So how did you do? How do you find the matrix representation of a linear transformation with respect to canonical basis? First of all, what is canonical basis?
0, 1, 1, 0. Right?
Yes, yes. See, when you change the order, the matrix will change. So don't change the order ever. Okay, always keep the order as it is. Otherwise, the matrix will change. So that's why sometimes we call it ordered basis. Okay, specifically we said ordered basis. So the order is always 1001. Okay, so if it is 1001, okay, how will you form the matrix? So suppose you have some transformation T. Suppose you have some transformation T, okay, from V to W. How will you form the matrix? The matrix of T, or you can call it M of T if you want. You write it as the first column is from T1, the coordinates of the coefficients of T1, the coefficients of T2, and then the TN. Correct? This is how you write. You remember? Yes? You find what is T1, T2, and so on, and just write them as the columns. Right? So the same thing you are doing here also. You find what is TW of 10. What is TW of 10? What is the definition? It is TW of V is V dot W, right? So here V is 10. So 10 dot W, which is W1, W2. What is their dot product? Yes,
W1.
W1. Now what is the dot, what is TW of 0, 1?
W2.
Okay, so you see that your M of TW is, you have TW of E1 and TW of E2, which is nothing but W1, W2. That's all. So this is your M of TW. Okay, just the W itself, the vector which is fixed, that itself gives you the matrix. Okay, fine. Okay, so here are some specific examples if you want. So TW of 1 comma 2, where W is 3 comma 4 is given here. Here W the same 3 comma 4, but for a different vector it is done. Okay, fine. Now let us look at the same transformation in C2. Okay, in C2 the definition is same, but the dot product, you know that in C2 it has a complex conjugate for the second argument, right? So that is the difference here. So now suppose you have a fixed W and you have a V. Okay, so then you have these as the images. Now can you tell me what is the matrix representation of this? Exactly same process. So in the case of real, what was the matrix? The matrix was simply given by, yeah,
W2.
exactly. Now I'm saying the answer is exactly the same. So tell me what is the matrix representation for this in C2? The answer is the same.
V1 W1, right?
Okay, so
Complicated.
let's see. Let's see. Okay. So the answer is going to be exactly the same. Let's see how. See, you have, what is a matrix of TW with respect to canonical basis? So this is your TV. Okay. Now MTV is given by here TV of E1. So this is your TV of E1. So according to the definition, it is E1 dot V, and then this is TV of E2, which is E2 dot V. Okay. Now what is E1 dot V and E2 dot V? It is simply V1, V2, right? It is simply V1, V2. Does anything change here?
Yes.
What does change? What does it change? What changes here?
Ma'am, it will be V1 bar and V2 bar.
Yes, there is a bar here. That is the only difference, right? So here, for example, you see that. So if you are taking the real case, nothing has changed. But when you change, when you take this imaginary values, what was M of TW of V? This was your TW of V, right? So let me write what is TW of E1. So what is TW of E1 according to this definition? So this is your definition, right? It is E1 dot W, which is 10 dot, your W here is 2 plus I comma 1 minus I. So here you have 1 times of 2 minus I plus 0 times of 1 plus I. So what is that you have? Simply 2 minus I. Same way you can easily compute and check that TW of E2. Without computing, can you tell me straight away what will be the answer for TW of E2? So 2 plus I became 2 minus I. So what will be to TW of E2?
1 plus I.
1 plus I, right? So you see that TW of E1 is this and TW of E2 is this. So what have you got? This one is W1 perp and this is W2 perp. So what is the matrix representation of TW when TW is from C2 to C? It is W1 bar, W2 bar. That's all. Okay, since it is complex, you are having the complex conjugate. Otherwise, it is exactly the same. Okay, fine. Okay. So the next concept is conjugate transpose of a vector. Okay, conjugate transpose is nothing but, so for example, let us say you have 2 plus I, 1 minus I. This was the vector we had earlier also, that's why I took the same example. What is the complex conjugate of this vector? What is the complex conjugate of this vector? The whole bar if I'm doing, what is the answer?
2 minus I and 1 plus I.
Exactly. So it is 2 minus I and 1 plus I. Okay, now I want to take the transpose of 2 minus I and 1 plus I. What is the transpose of this? So it is, this is actually having this representation, right? 2 minus I, 1 plus I. What is the transpose of this? So this is now, what is the size of this matrix? Can you tell me?
2 by 1.
This is a 2 by 1. Now what is the transpose of this vector?
1 by 2.
Yeah, the same in a row. Okay, so now what is the conjugate transpose of a vector? You have to do the conjugate and also you have to do the transpose, that's all. So conjugate transpose means you have to do both. So 2 plus I, 1 minus I, transpose bar, both are there. So the answer is simply 2 minus I, 1 plus I. That's all. Okay, so here you see that this, here in fact we see that here they are giving in terms of m of tv. So m of tv is v1 bar, v2 bar, that's what we have written here. So you see that this is the complex conjugate of any given vector v. So for a given vector v, m of tv gives the complex conjugate. Okay, fine. So you don't have to go to m of tv for that. It is a straight away process. You can straight away do from here. You don't have to go to m of tv for that. But it is just explained through m of tv in this scenario. That's all. Okay. So what is the conjugate transpose of a vector? Is that clear for everyone? Yeah. Okay. Good.
So basically, the transformation is simply the complex conjugate, right? When it is
Exactly.
complex. Okay, so
Exactly.
that's what the significance of this. So,
Yes, yes, yes. Okay. So now we are going to see the matrix representation. We already know, given a linear transformation, how to find the matrix representation for a canonical basis. We already know. Now we are just going to see it in terms of dot product. That's all. Okay. So what is the matrix representation of this T with respect to E1, E2? The first column contains TE1 and the second column contains TE2. This is what we already know. Is that correct? Yes. Now, what are the coordinates of TE1? How will you find the coordinates of TE1? In terms of dot product, how can you tell? See, this is just E1 and E2, so straight away you can tell, or you can beat around the bush and go back to this orthogonal transformations and tell from here. That is also there. So what is the one property we have seen here? This one. Okay. So here the coefficient of, so here x is equal to w dot u and y is equal to w dot v. This is one thing you can use. Okay, so how can we use that here to see this? See, E1 and E2 are obviously orthonormal basis. Okay, this obviously forms an orthonormal basis. If this forms an orthonormal basis, then you know that TE1, this is your W here. The coordinates are TE1 dot E1 times, here you have again in terms of E1 plus TE2 dot E2 into E2. So these are your coordinates from that concept we have seen earlier. Do you all agree with that? Yes or no? How did we write this? Can you all understand? Yeah? If it's not clear, please
Yes,
just
ma'am.
explain. Is it clear? Okay. So if there is no response, I assume that it is clear for everyone. Okay. So now you see that TE1, we have written it in this way. Okay. Now you see that if this is these are the coordinates of TE1, the same way you can generate the coordinates of TE2 as well. Right? So for TE2, in place of TE1, you will have TE2. So here, sorry, here there is an error. No one mentioned. So here it is TE1 dot E2, right? So analogous expression, if you want to remember, W is equal to W dot U times U plus W dot V times V. This was the analogous expression if you remember. Okay, where U comma V is an orthonormal basis. Okay, so you see that these are the coordinates of TE1. Same way you can see these are the coordinates of TE2. So instead of TE1, I'm writing the coordinates of TE1. Instead of just TE2, I'm writing the coordinates of TE2. So the matrix of T with respect to E1, E2, how I wrote in terms of dot product, is that clear for everyone? How did we obtain this matrix? Is that clear? Yes? Yeah? Okay. No one responding. Okay. So now in that case, you can see that you can write TV as this matrix times of V, because this is the matrix representation of T. So TV is simply the matrix times of V, right? Okay. So there is another new concept which we are going to see, which is called as functionals. What are functionals? Functionals are simply functions which takes values from C2 and maps it to scalars in C. Okay, how are we defining these functionals? By fixing some vector in C2 and doing the dot product in this way. So f of v is equal to tv times of u, where t is a linear transformation from C2 to C2. So this is the linear transformation we are considering, and f of v we are defining through this linear transformation. F of v is tv dot u. Okay. So we have, see, for defining this functional, we have used two things. What are they? We have used a linear transformation, and we have also used dot product to define a functional. All right. So this functional is a very important topic. In fact, there is a separate course called functional analysis. Okay, fine. Okay, so here what is this f doing? Let us see. Okay, now f of v, you see that f of v is t of v dot u. This is the definition. Now what is v? You have the canonical basis e1, e2. So v can be expressed as v1 e1 plus v2 e2. Same way u can be expressed as u1 e1 plus u2 e2. So I am replacing v and u with these expressions here. Okay, what's the next step? When I do the dot product in C2, you know that the second argument gets a bar. So that's why you see here. Now, first of all, this part here, you see that it becomes, now this one, first of all, you apply the linear transformation. So you get V1 TE1 plus V2 TE2. And then you dot product with U1 E1 plus U2 E2. Right? Then you do the dot product. So you see that V1 U1 bar TE1 dot E1. Okay. And then same way plus V1 U2 bar TE1 dot E2. And then V2 U1 bar TE2 dot E1. And then V2 U2 bar TE2 dot E2. So this is just dot product we have done here. Then here we are doing some rearrangements. That's all. We are just taking complex conjugate. For example, for the first term I'm telling. So the first term, what is happening? You have u1 bar. You have u1 bar te1 dot e1. Right? Now this term, can I write it as u1 te1 dot e1 bar whole bar? Will they be same? You know that z bar whole bar is z, right? We are just using that property here. Okay. So we are just using the properties of complex conjugate here. So this equality is fine for everyone, right? We are just applying that here for both these terms, for this term, and then we are using it for this term. So for this and this only, so that v1 is taken out in both the term. So we are just taking the v1 in both the terms and then taking the complex conjugate. Same way we are taking the v2 commonly from here in these two terms and doing the complex conjugate for the whole term. Okay, then what is done? We are simply writing these terms in terms of a matrix. So you see that now this and this expressions are same. Te1 dot te1 bar u1 plus te1 dot e2 bar u2. Same way you get the second expression. Okay, and then you have v1 v2 here as dot products in the front place. How did we get this expression? These are some simple calculation. Do you all understand how this calculation is done? Any doubts in these calculations? Clear for everyone?
Yes, ma'am.
Okay. Fine. So now we are trying to define what is called the adjoint of an operator. These are some preparatory steps. You can see that they are kind of unrelated things I am telling next to next. But you see all these are kind of preparatory steps to define the adjoint of an operator. Okay, let's see how. So now we already saw what is conjugate transpose of a vector. The same goes for a matrix as well. So if you have a 2 by 2 matrix, the conjugate transpose denoted by A power H, okay, is given by, here you see first we are taking what is A transpose. Can you tell? A, what should be here? What should be here when you take the transpose?
C.
C, B, and D. Right? So this is the transpose of the matrix. Now we are just taking the conjugate, a complex conjugate of this transpose. So conjugate transpose means you take the transpose and take the conjugate. That's all. Or you take the conjugate and take the transpose. Both are same. Okay. So now you see that, note that in the above expression for f of v, okay, in this expression, what is this term? What is this here? This expression here. What do you notice here? This is the matrix we saw here, right? This is the matrix we saw here, and the complex conjugate is present, right? So you see that f of v is this expression where this matrix here is nothing but the conjugate transpose of m of t, right? So we can write this t of v is equal to m of t. We already have t of v is equal to m of t of v. And also from this expression here now, f of v is equal to, from this definition, this is t of v dot u. This one. This is tv. This is your tv. And here, this is the expression we just obtained from here. Okay, I maybe call this as equation 1. Okay, so from 1. This is from 1. Okay, so you see that this is m of t and this is the complex conjugate of this matrix. Okay, so you see that here we are having tv dot u. Here we are having tv dot u, and here we have v dot. Here we have some matrix. You don't know what is that matrix. Like matrix representation of some transformation, you don't know what is the transformation. This is a matrix you have, you don't know what is the transformation it is representing. Here this is m of t, and what is this representing, you don't know yet. So I have just put a box. I will tell you the name of this just right now. So that is called as the adjoint of the operator. So what is the adjoint of the operator? The linear transformation t star from c2 to c2, okay, is the adjoint of t represented by this matrix, and it satisfies this condition. tv dot u is equal to v dot t star u. So this is T star U. So this M of TH, the complex conjugate, is the representation of this particular transformation T. Is that clear? This is just the definition. Okay.
Yes, ma'am.
So usually we are having a matrix from a transformation. Now we have defined this operator or the transformation from the matrix. First we obtain the matrix, and from the matrix we are defining what is the adjoint operator. Okay. So you see that for every vector v you have tv, and for every vector u in C2 you have T star u. Okay, fine. So here are some examples. Find the adjoint of the following operators. It's very easy, right? How do you find the adjoint? If you find m of t of t power h, you know the adjoint operator, right? So to find the adjoint, you need to find, what is that you need to find? M of t of h. So I'll just do for the first one, you do the problem 213. For the first one, can you tell me what is m of t? Can you tell what is m of t? How do you usually find m of t? 1, 2, 2, 3, right? So you simply write what is TE1 and TE2. That will give you m of t. Now what is m of t whole transpose? It is m of t itself in this case, right? It is.
Yes, ma'am.
So also you notice that m of t, if you take the complex conjugate, here there are no complex terms, so nothing is going to change. It remains the same, right? So your adjoint operator T star P is given by m of t power h v. So where m of t power h is nothing but m of t v in this scenario. That's all. Okay. Now I give you time to complete 2 and 3. 2 is very straightforward. 3 it will take little bit of time. I just give you some hint to complete 3, and I'll give you time also. So for completing 3, you need to solve some system of linear equation. What are they? First of all, you need to express 1 comma 1 and 1 comma 2 in terms of E1 and E2. Or the other way around. I'm telling it the wrong way. So I want you to write E1 in terms of 1 comma 1 and 1 comma 2. Same way E2, the expression should be found for this. Find alpha 1 beta 1 alpha 2 beta 2. Then you can just apply the transformation on both sides and find TE1 and TE2. Okay. So everyone try to complete 2 and 3. We'll have a short break of 5 minutes. Meanwhile, you try to complete this problem. Okay. Everyone, please try to do the problem. So how many of you have completed? Okay, what's the answer? Only one hand I see. What about the others? Did you not complete? At least 2 is straightforward. What is the answer for 2? What is m of t power h?
1 minus I and minus 2I and minus 2I and 3 minus I.
Okay, so you have 1 minus I, minus 2I, minus 2I, and 3 minus I. Right. Okay, what about the third one? Did you find what is alpha 1, beta 1 and alpha 2, beta 2?
Ma'am, alpha 1 is 2 and alpha 2 is minus 1.
So you are talking about this alpha 2, or how did you take the alpha
Yes,
beta?
ma'am. Alpha 1 is 2 and beta 1 is minus 1.
Okay, so let's quickly check. So 2 minus 1 is 1 and 2 minus 2 is 0, correct? What about alpha 2 and beta 2?
Alpha 2 is minus 1 and beta 2 is 1.
Okay, let's see. So minus 1 plus 1 is 0, and then minus 1 plus 2 is 1. Good. So this answer is correct. So now you know what are the coefficients. Now what is TE1? TE1 is 2 times of T of 1 comma 1 minus 1 times of T of 1 comma 2, and TE2 is minus T of 1 comma 1 plus T of 1 comma 2, correct? So what is T of 1 comma 1 is 1 comma 2, and T of 1 comma 2 is 2 comma 3, and here 1 comma 2, 2 comma 3. So did you all get the same answers? Like here 2 minus 2 is 0, 4 minus 3 is 1, and here you will get 1 comma 1.
1.
Did you all get the same answer? Yeah. So you know what is TE1 and TE2. Now what is M of T? M of T is 0, 1, 1, 1. And what is M of TH? What is the answer? What's the answer for M of TH? The complex conjugate? Same, right?
Same.
Okay. So how to find the adjoint of an operator? Is that clear for everyone? Yes?
Yes, ma'am.
Okay, fine. So suppose you have to specifically write what is T star V. How will you do? For example, in this case, how will you write T star V? V, let us say it is V1, V2. How will you write T star V? You have found this.
Adjoint multiplied by V.
You just have to multiply it with V1, V2, right? So you have to take 0, 1, 1, 1 and multiply it with V1, V2. That's all. So you will get V2, comma V1 plus V2. This is T star V. Okay. This is how you, if you want to specifically write, this is how you will write. Okay. Clear?
Yes, ma'am.
Okay, good. So only Chirag answered. I see Arpit, Akash, Ashish have done some conversation. What about the others? Anyone? Randomly calling some names. Arjit, Ankit, Bittu, Christy, Jatin, Iba, Saravanan, Maki. Are you all there? Are you all listening first of all? Prakhar, Pranav. So many names. I'm just randomly calling some names. Tanishka, are you all listening or not?
Yes, madam. Listening, madam, and working on it, madam. And yeah, we had the answers also, madam.
Good, good. As long as you follow, I'm happy. Good. Okay. So the next topic is we are going to see 4 important subspaces. Okay, 4 important subspaces of R2. Okay, so what are they? Let us see. So first let us consider a matrix A is equal to A, B, C, D. Okay, now what is A transpose? A transpose is simply A, B, C, D. So since it is an R2 T star, here there is nothing to do. Complex conjugate has nothing here. So transpose simply gives you T star, right? Now what is the column space of A? It is the span of the column vectors of A. So the span of AB and CD. Same way, what is the column space of A transpose? Span of AC and span of BD. But what is it you can notice? AC and BD forms the rows of A. So column space of A transpose is same as the row space of A. So these two spaces are same. Is that clear? That this
Yes, ma'am.
okay, fine. So the next thing is that what is the null space of A? The null space of A is nothing but this is your A set of all x comma y such that A times of xy is 0. So when you write this in terms of equation, you will get ax. So what is that? You will get ax plus, maybe I'll write it in yellow, otherwise it won't be visible. Ax plus cy is 0 and bx plus dy is 0. All right. So you see ax plus cy is 0 and bx plus dy is 0. That is same as the dot product of xy with ac. So you get ax plus cy, and here you see that x comma y dot product with bd, you will get the second equation. Okay, so we have returned the system of linear equation in terms of dot product here. Why did we write so? Let us see here. See, now what is the column space of A transpose? Let us write what is the column space of A transpose. What is the definition of column space of A transpose? This is the column space. Okay, it is already there. Now, what is the orthogonal complement or the dual of column space of A transpose? So, it is the set of all x comma y, right, such that your x comma y is orthogonal to both these spanning vectors. It is orthogonal to A comma C and orthogonal to B comma D, so that the dot product is 0. Okay, so you see that these two are exactly the same, right? So it means what? The null space of A is same as the orthogonal complement of column space of A transpose. Okay, column space of A transpose orthogonal complement is same as null space of A. So is up to this, is it clear for everyone? First of all, we saw that column space of A transpose and row space of A are same. Then we see that null space of A is same as the column space of A transpose complement, orthogonal complement or the dual. Up to this is clear for everyone? Yeah.
Yes, ma'am.
Now, can we do something similar for understanding this as well? The column space of A transpose is equal to the null space of A perp. How can we check this? What do we already know? That so let us write what we already have. We already have column space of A transpose orthogonal complement is equal to null space of A. This is what we have. Now, if I am going to take the dual again, we have already seen this property, right? If I am taking dual again, then what happens? The space will be again the same, right? So it will reduce to just column space of A transpose, correct? So that is what is written here. How did we get this? Is that clear? Just by taking a dual again for both the spaces, you will get this. Is that clear? Yes? Okay. Fine. Now, let us look at the same thing in case of C2. In case of C2, now you have the column space. These are the column space A, B and C, D. and the column space of instead of A transpose, now I'm having the complex conjugate transpose. Conjugate transpose I am taking, and now you see that column space of AH is given by A bar, C bar, B bar, D bar. Okay. Now you see that it is equivalent to the row space of A bar, right? What is your A bar? A bar is nothing but A bar, C bar, B bar, D bar. Okay, so these are the rows of A bar. You can see that, right? And the null space of A, we have already seen this expression. Only thing is that here, what is that you have? You have AX plus CY is equal to sorry. So here the null space of A here is AX plus CY is equal to 0 and BX plus DY is equal to 0. But instead of AX and BY, here we are having A bar X plus C bar Y and B bar X plus D bar Y. Why is that so? So in this side, it is very clear because here this is what we are having. A bar, C bar and B bar, D bar. This is what we are having, and we are taking the set of all vectors orthogonal to the spanning vectors. So this side it is clear. But why we are taking bar here? The null space of A, instead of just taking the matrix itself, I am taking the complex conjugate of the matrix and then I am performing it. Why is that so? Null space of A, is there something we are missing here? Null space of A, why are they same? Here, what is that I am missing? Equivalent to row space of A bar. I don't immediately see what I'm missing here. But anyway, for now, let us hold on to this. I will check this and tell you. Okay, so at least this side it is clear, right? That the column space of A bar H complement, the dual is given by this. Okay, here they are trying to say that the null space of A is same as the column space of A, the null space of A and the column space of AH complement, orthogonal complement, they are same. So here you see that when they take the perp on both sides, they are same. Okay, but here why these two are same, I have not completed this. Let me check this and get back to you. Maybe I will add this proof before uploading the PDF, before giving this PDF to you. I will add the details here. Okay, fine. And then you see that row space and column space in general, they have the same dimension. Why is that so? Why the row space and column space, the dimension is the same? In fact, how many of you have seen the definition of rank of a matrix? How many of you have heard the definition of rank of a matrix? Anyone who know what is the rank of a matrix?
Independent columns or rows?
Number of linearly independent columns, right? Or
Yep.
rows. So always the number of linearly independent rows or columns are going to be the same. That is what is mentioned here. Dimension of row space of A and dimension of column space of A are same. The question is why? Why they are same? Okay, let us see. We are using two concepts to understand this. Okay, one is rank nullity theorem. Do you all remember what is rank nullity theorem? What is rank nullity theorem? Rank of T.
Rank plus nullity, right?
So you have a
Dimension.
transformation T from V to W. So rank of T plus
nullity.
nullity of T should be equal to
2.
Yeah, so here if your V is R2, then it will be 2. Otherwise, it is simply dimension of V. Okay, the other thing we are going to use is that dimension of, so let us say you are having working only in R2. Okay, so in that case it is 2. So let us say you are having some subspace. S is a subspace of R2. So you know the dimension of S plus dimension of S perp is equal to 2. This also we have. So we are going to use both of this now. Okay. So now you see that dimension of row space of A is same as the dimension of row space of A bar. So here taking the complex conjugate is not changing the dimension. So when you are doing the bar, you are not missing out the linear independence. Linear independence is still going to be there, right? Linear independence is not affected by the complex conjugate. So the dimensions are going to be the same. So in that case, row space of A bar, you see rows, it's nothing but now column space of AH is same as null space of A dual. That is what we are having here. Now what is the next thing we are having here? Dimension of null space of A dual. This one is, we are using this property here. Okay, so this is 2 minus dimension of the null space of A. So here S is your null space of A. So what is this? This is your S now. So you are taking dimension of S perp is 2 minus dimension of S. Okay, and then now you are using the rank nullity theorem. Now you know that dimension of null space is 2 minus rank of A. Now rank is nothing but the column dimension of the column space of A. So 2 minus 2 minus dimension means you will simply get dimension of column space of A. Okay, so what is it you have got? You have got that dimension of null space of A dual is same as dimension of column space of A, and we already know that these two are same. Okay, so here what are the basic spaces we are looking at? What are the 4 fundamental spaces we are looking at? We have seen what is the column space. The first one is the column space we have seen. This we have seen. What is the column space? You know, the span of the columns. What is the null space? We have seen. What is the row space? We have seen. And then what is the left null space? That is the only thing we have to see. Let's see that also. Now, before that, there is one important thing about subspace and its dual. What is subspace and its dual? So, a subspace S in C2 or R2 and its dual S intersection, what is there in their intersection? And means here we are talking about their intersection. What is there which is common in both? It is only the zero vector. Why? How? So let us say that you have some vector V in S intersection S perp. So V is in S as well as V is in S perp. So now what is the definition of S perp? S perp is the set of all U in R2 or C2 such that U dot V is equal to 0 for all V in S. This is the definition. Now here you see that your V is in S perp. Okay, your V is in S perp as well as V is in S. It means what? You will get V dot V is equal to 0. Right? You will get V dot V is equal to 0. So when according to the positive definite property, what do we know? So by positive definite property, we know that if V dot V is equal to 0, then V is equal to 0. Right? So it means what? In the intersection, we have only the 0 vector. Okay. Already we have seen that the dual of this space is same as this space. So instead of dual, I am writing just this space. Okay, null space of A intersection column space of AH is equal to 0. I am just using the previous property here. S intersection S perp is 0. Right? Now we know that null space of A perp is equal to this one. Right? So that's why we are getting this property. Same way this also. Okay. So these properties we have obtained from the dual properties of each of the spaces. So what are the four fundamental spaces? Column space, null space, row space. And what is this left null space? Okay, so left null space is nothing but the null space of A transpose. Okay, how is that so? So what is the null space of A transpose? Null space of A transpose is A transpose U is equal to 0, and left null space of A is nothing but, this is the definition of left null space of A transpose. How these two are same? How these two are same? You see that A transpose U is equal to U1 U2. Now what is A transpose of U1 U2? Your A transpose is given by this matrix A, C, B, D, and you have U1 U2. So you are ending up with AU1 plus BU2, and then you have CU1 plus DU2, right? Now, what is U transpose of A? U transpose means you have U1, U2 times of A. What is A? A, C, B, D. So what is that you will get? What is the vector you are getting here? U1, U1 times of
A.
or AU1. Let us write it as AU1 and then plus BU2. Just to compare, it is easier, that's all. And then you have, so what is the size of this matrix? This is a 1 by 2 matrix and this is a 2 by 2 matrix. So remember, the resulting size is also a 1 by 2 matrix. So the other vector should come here. So U1, U1C, so which is CU1, and this is plus DU2. Now saying that this is equal to 0 means these two are 0. Right? This value is 0 and this value is 0. It is same as saying this as 0. Right? Both are equivalent. You see that both are equivalent. These two are equivalent. Okay, same way you can also see that these two are equivalent. U transpose A and A transpose U, they are equivalent. Okay, so the left null space of A is nothing but almost same as the null space of A transpose. It is exactly, in fact, same as the null space of A transpose. Okay, fine. So we are going to look at what are the four subspaces of four main subspaces, fundamental subspaces for any matrix. That is what we have seen so far. So specifically for these examples, how to find the fundamental subspaces, it is a very simple task only. Let us do for the first problem, and I will tell you to do these two problems and see how far you are able to complete. So for the first problem, what is the column space? First of all, for let's call this to be A, and maybe this is B and this is C. What is the column space of A? It is the span of 1, 2, 2, 3. Is that correct?
Yes, ma'am.
Now, what do you know about these two vectors? Are they linearly independent? Are these two vectors linearly independent?
Yes,
Yes.
ma'am.
So if they are linearly independent, what is the span of two linearly independent vectors in R2?
R2.
Yes. So if we have two linearly independent vector, their span is entire R2. Okay. The next space is the null space of A. How do you find the null space of A? In fact, you don't even have to find the null space when you already know the column space. But anyway, let's see what is the null space. So the null space is set of all x such that Ax is equal to 0. Without calculating, can anyone tell what can be the answer? What can be the answer? The whole space is your range. So
Ma'am,
what?
0.
Yes, yes. Rank nullity theorem gives us that, right? Okay, let us also verify it quickly. So here you see that you have 1, 2, 2, 3. Xy is equal to 0, 0. So it means what? You have x plus 2y is equal to 0, and you have 2x plus 3y is equal to 0. Okay, it means what? Here we have to solve these two equations. So if we solve these two equations, what is that we will get? 2x plus let's say 4y is equal to 0. I'm just multiplying the first equation with 2 and then I'm keeping the second equation as it is. Then when I'm subtracting, I get y is equal to 0. If y is equal to 0, I substitute here, then I know that x is equal to 0. So you see that x comma y is xy is 0 vector. So this is nothing but the 0 vector, right? Okay. What is the row space of A? Again,
Span of 1, 2, comma 2, 3.
it is again the same as the column space, right? And what about the left null space or of A, or let us say the null space of A transpose, right? That is what we have seen. See, left null space and null space of A transpose are same. So let us compute what is the null space of A transpose. So what is the null space of A transpose? Do you already know the answer? See, this is nothing but we already know this is the column space of A transpose, right? So if we know the column space of A transpose is R2, so what should be the null space of A transpose?
Origin.
0.
0, right? Okay. So now we know that these two are linearly independent. That's why we got it to be R2. Now, what do you observe in the case of B? What do you observe in the case of B? So, are they linearly independent?
No, ma'am.
These two are linearly dependent. If they are linearly dependent,
Dependent.
what will you get as a span?
1. Line passing through the origin.
Yes, it is just the line passing through origin. Specifically, it is, what is this? Can you tell? The set of all x comma y such that, yes,
Y equal to 2x. Yeah,
y is equal to,
2x.
are you sure? That is y is equal to 2x only, right? Yeah. So you get y is equal to 2x. So when x is equal to 1, y is equal to 2. So you get 2x minus y is equal to 0 equation. So this is the column space of A. Now if this is the column space of A, how will you find the null space of A? You definitely know it is not the 0 space. It is going to be some other straight line. So we have to find what is that. So set of all x such that Ax is equal to 0. So how are we going to find this now? Can anyone tell how are we going to find? See, null space of A is same as column space of this one, right? So here, what is your A star or A transpose? What is your A transpose? The dual of that you can take. Okay, so either you can find the dual or you can find the null space. Both are up to your convenience. Anyway, the equation you are finally going to get is exactly the same equation only. Nothing will change whether you take the orthogonal complement or you write the definition of null space. You will get the same equation, which is x plus 2y is equal to 0. So what are the solutions of this? That is going to give you the set of all here x comma y such that x plus 2y is equal to 0. This forms the, maybe here instead of x I should write u or v, something like that. U such that au is equal to 0. So it is set of all x comma y such that x plus 2y is equal to 0. Can you see that these two, what is the relation between these two? Can you see? What is the relation? So you have 2x minus y is equal to 0 and you have x plus 2y is equal to 0. So you have 1 comma 2 here. And suppose I am taking 2 comma minus 1, it is satisfying this. They are orthogonal complements, right? Yeah. Okay. So the next thing here is
One thing, excuse
yes.
me. The left null space of A equal to null space of A, right? You represented
Left null space of A is same as null space of A transpose.
Yeah, A transpose. Should it be represented as 0, 0? Because it's a coordinate, right?
It's understood that sometimes we don't write always.
Okay.
It's understood. That's all.
Okay.
Okay, fine. So now you see that row space of A is the next thing we have to find. Again, the row space is going to be the same. You have 1, 2, 2, 4. So it's going to be again the span of 1, 2 only. It's nothing has changed. Okay, nothing has changed. So you will see that for null space of A transpose, again you are going to get the same space. Okay, so nothing will change for null space of A transpose here. So you will get a similar answer like this. You can check that. Okay, so find null space of A transpose and verify what you are getting. So here, is there anything you can observe?
Yes, linearly dependent.
They are linearly dependent, right? And if they are linearly dependent, the same technique you can use. So 3, I am giving you as a homework. Try to do it yourself. If you are not able to complete it, then we can try it out in the next. If you have any doubts, like you try to complete it, it's nothing big, it's very simple, just like this. If you have any doubts, we will try to complete it in the next session. So what are the topics we have seen so far in today's session? In today's session, we have seen, we have completed this part, we have completed this, we have completed this, and we have completed this. What are the operations with adjoint eigenvalues and eigenvectors of an operator and its adjoint least square fit? These are the things which are left, which will be covered tomorrow or Monday, I guess, right? Okay, fine. So in today's session, except that one part which I tell, I will update. Are all the other parts clear for everyone? Okay, fine then. Good. So,
Too much of things. I think lot of it's compressed.
but one
many
thing you
many.
should be happy about that you are not given all the general vector spaces. You are only given R2. That you should be very happy. Only you are dealing with 2 by 2 matrices. Imagine if you are given with general vector space. That is what as a math student, that is what we usually do in BSc. In BSc, all these concepts we study for general vector spaces. So that vector spaces includes Rn, all the polynomial spaces, all the matrix spaces, so all the functional spaces, continuous functions, so many things are there. So you must be very, very happy that it is limited to R2 so that the computations are very simpler for you. Yes, I agree that there are so many concepts, but one thing you should be happy that the computations are very simple. As long as you remember the concepts, the computations are simple. Okay, fine. Maybe you all should have some set of examples, like 1 or 2 examples for which you know everything. Okay, for example, let us say what are the concepts we are having. Okay, so inner product means inner product in R2 C2. It means at least you take 2 vectors, you write what is the inner product for R2 and C2, what is the magnitude of one particular vector, distance between any 2 vectors. So like this, for each topic you try one example, just one example for every topic. So whenever you want to recall week 4, just open those examples. You will quickly and remember what are these topics, what is the topic telling you. You don't have to just read the entire thing. Just one simple example will help you understand. You may not cover everything, but that will give you, try to help you to remember the topic. Okay, just
Correct,
try
do
to do that. Okay then.
Yeah. The numerical problems are okay. I mean, we can understand, but maybe some of the underlying concept, I mean, how in physically how it signifies all those things. Maybe
The
yeah,
physical
I have to read a lot.
significance is a very, very difficult thing to understand. See, geometrical property in R2 you can understand, but the thing is that every time you have a problem, how are you visualizing it? That you have to do it right from the beginning. Every time, every single time. Let us say you are having 2 vectors. If you are if you see this statement, then you should have a picture of R2 and you should see 2 vectors in R2. If you practice this every time, or if that imagining is difficult for you, just always keep a paper and pen with you. Okay, always in that paper draw 2 vectors. In that way, you will automatically, when you see the statement itself, you also see the visualization along with it. Okay.
Thank you.
Okay. Okay, fine. So see you in the next session, maybe on next Saturday. Maybe. Thank you, everyone. Bye.
Thank you, ma'am.